Okay, so hello everyone. My name is Peter. I'm from Netcope Technologies. Netcope Technologies is a small company from Czech Republic. For those of you who haven't been to Prague, I'll just say that we share our western border with Germany. Going back to our company and what we do, we are a startup company which is focused on using FPGA technology to accelerate data processing at high bandwidth. We are quite young. We are 2 years on the market, but the history of the people who are behind the company, who work in there, goes 10 years back. So we've got a pretty good experience with FPGAs and how to accelerate data workloads. What are we typically dealing with and trying to address is the growing bandwidth or the workloads in the networks. And for that, we believe that the combination of flexible software running on CPUs and let's say data plane acceleration in the FPGA is the right combination. During that, for that purpose, we have over time developed a set of various building blocks for the FPGA, including packet header processors, various lookups and classification engines, and obviously some packet editing tools or IPs as well. We kind of connected together with the network interfaces as well as software interfaces like DPDK, which is very good for software processing and leaves some space for optimization on the PCI Express, which we address using the NDP API as our proprietary API. And all these building blocks kind of, as you can see, handle packets in some way. Now, we have been able to address various applications using these IPs, and nowadays we see a lot of change towards the virtualization, right? So we've got a virtualized compute storage, and now we are seeing virtualized networking, where the OVS is a key component. So it would be very cool if we could use our building blocks to accelerate the OVS and bring it to 100 gigabits or 400 gigabits. Luckily, people from Stanford around Nick McKeown came up with a language which kind of gives an umbrella to all of these operations, and we created a compiler of P4 language to VHDL, which is a hardware description language, and this compiler allows us to kind of compile all of the building blocks into an FPGA. The pipeline, which is on this slide, is the same as for any other P4 implementation. In our case, we had some other, let's say, issues or challenges that we had to address, like mapping of the P4 language into the FPGA. So, for example, what we typically deal with is a trade-off between the latency, throughput, and the space or resources consumed on the FPGA. So we have created various implementations, for example, of the match action tables, and with the naive approach of ternary content address memories, we can get pretty good results, but these building blocks are quite expensive in terms of area. So we are looking into other implementations using hashing functions, Bloom filters, and so on to improve the performance and capacity of the match action tables so people can really do much more in the FPGA. At the end, what we hope for is really simplified the data processing, where the FPGA would take care of the whole, let's say, data plane for the megaflows We sometimes call them heavy flows. So there's a lot of work on our side that we would like to do. And if there's anyone who has questions, who is interested in running some OVS code in FPGA, please feel free to talk to me. Thank you.